Howdy, it's Mr. Russell and coming at you today with limiting reactants and percent yield. Notice that I said limiting reactants. This definition right here says limiting reagent. Those two can be used interchangeably. It is a reagent or reactant that limits the amount of product that can be formed. Anytime you are given the amounts of two or more reactants, you'll need to try out each one to see which one is the limiting reactant. That's the one that's going to limit your reaction. The easiest thing to do is to work all of them, and all you have to do is go as far as the moles and then take the one that's the smallest value. To get a visual idea, let's watch this animation.
Nitric oxide, NO, is produced when atmospheric nitrogen and oxygen react at high temperatures in an automobile engine. Once released into the atmosphere, nitric oxide is quickly oxidized to nitrogen dioxide, NO2. Nitrogen dioxide is a toxic brown gas. Much of the brown haze present in photochemical smog is due to the presence of nitrogen dioxide. The left side of the two-bulb vessel contains nitric oxide gas, NO, and the right side contains oxygen gas, O2. Click on one of the buttons to choose the number of molecules of NO you would like to react with the number of molecules of O2. Nitric oxide and oxygen gas are reacted in a 1-to-1 mole ratio. There are 4 molecules of NO in the left bulb and 4 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2 producing 2NO2. 4 molecules of NO are reacting with 4 molecules of O2. The 4 NO molecules require only 2 O2 molecules for reaction. Note the 2-to-1 mole ratio in the balanced equation. Therefore, 2 O2 molecules remain after reaction. The reaction stops once the nitric oxide gas runs out. NO limits the amount of product that can be formed and is therefore called the limiting reagent. Oxygen gas is present in excess. Nitric oxide and oxygen gas are reacted in a 2-to-1 mole ratio. There are 6 molecules of NO in the left bulb and 3 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 6 molecules of NO are reacting with 3 molecules of O2. They are reacting in a 2-to-1 mole ratio as represented in the balanced equation. No reactants remain after the complete reaction. Nitric oxide and oxygen gas are reacted in a 3-to-1 mole ratio. There are 6 molecules of NO in the left bulb and 2 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 2 molecules of O2 are reacting with 6 molecules of NO. The 2 molecules of O2 only require 4 molecules of NO for reaction. Note the 1-to-2 mole ratio in the balanced equation. Therefore, 2 NO molecules remain after the reaction. The reaction stops once the oxygen gas runs out. O2 limits the amount of product that can be formed and is therefore called the limiting reagent. Nitric oxide is present in excess.
So to explain this animation, we had 3 blue buttons on the bottom. On the left one we had 4 NO and 4 O2. That means that the NO, the nitrogen monoxide or nitrogen oxide, was our limiting reactant, so we had oxygen left over. The button in the middle had an ideal mole ratio where we didn't run out of anything. We had twice as many moles or twice as many molecules of nitrogen oxide as we did oxygen. And on the right button, we had 6 nitrogen oxides and 2 oxygen molecules. So now oxygen was our limiting reactant and we had nitrogen oxide left over. I want you all to try this non-chemistry related problem where if we're just, say we're working at Subway and we've got we can every sandwich has to have 2 pieces of bread, 4 pieces of meat, 2 pieces of cheese, 3 pieces of bacon, and 2 ounces of special sauce. If I had all the ingredients listed, how many sandwiches could I make? So I bet a lot of y'all are wondering how many ounces are in a quart. Well, there's 32 ounces in a quart. So now can you do it? So your limiting reactant in this problem is going to be your bacon. It's going to be the 21 pieces of bacon because it takes 3 pieces of bacon here, so I would only be able to make 7 sandwiches. All the other ones you'd be able to make more than 7 sandwiches, so that's why bacon is my limiting reactant. There's never just enough bacon, is there? Now I want you to give this problem a try, and I want you to wait for the thing to go down, go away, okay. Where if we had a reaction where with x plus 2y yields xy2, and the x's are symbolized by the squares, the y's are symbolized by the circles, what would it look like after the reaction? Assuming that the reaction goes to completion. There are 3 squares and 8 circles. That means that for each reaction, I will need 2 circles and 1 square. When if I use the 3 squares together, that means I'm going to use a total of 6 circles. And so I will end up with 2 circles afterwards. I hope you got this. This is a valid AP test question where they will have you draw a particle view that looks just like this. Drawing squares for molecules and circles for other types of molecules. It's totally valid to put shapes on the test. So now let's do a mathematical example. Could you do this problem without my help? I have 3 different reactants and it's asking for only one of the products. The sulfur as a solid is just extra information so the equation balances out. And a neat trick or a neat tip to do is when you get your reactions, it's simple to just write the masses or the amounts underneath the equation so that it's visually represented. I'll go ahead and cheat a little bit and tell you that the water is the limiting reactant. To show this, I will take my stoichiometry I will take 2 moles of my water and then apply the mole ratio of water to my product that I'm looking for, iron hydroxide. Remember, these numbers come from the coefficients in the equation. So, and when I work it out, my answer is 1.3 moles of iron hydroxide. If you worked it out to where we had 1 mole of iron sulfide, we would find out, and also 3 moles of oxygen, we would find out that those molar values would be higher than 1.3. 1.3 is the least of the 3, so that is our limiting reactant. Here's an example in which I will not cheat, and I will show you all the steps. Go ahead and pause and read this question. Remember your tip. Go ahead and write down the amounts that are already listed. Since it gave us 17 grams of ammonia and 32 grams of oxygen, our unknown is going to be our reactant now. So Notice, that know their molar masses really well, these calculations are going to work out very nicely. Now, when we see we'll do our calculation with ammonia first, where we'll go from grams to moles, and we'll convert moles into our product that we're trying to find. This is the mole ratio here from the equation. And then we'll just convert moles of NO back to grams and come up with that. Now we'll do it again where we'll do it with oxygen. And they will go from grams to moles, and then we'll go from moles to moles again, the mole ratio from the equation, and then we'll get to our molar mass, convert, and we'll get to 24.0 grams of nitrogen monoxide. Now, which one is the limiting reactant? That's right, it's the smaller one. So 24.0 grams is the smaller yield, so oxygen is the limiting reactant, and 24 grams is the correct answer. It's the AP test is pretty good at giving you the problem, and students will take this first one and do the calculation and say that the yield was 29.9 grams, and they'll stop there. But unfortunately, we have to do it twice, and we have to reject one of them. We're going to reject this one and not include it. This is our value that we'll accept and write down, box in our answer, check, we got it right. So now let's discuss theoretical yield. So our lab isn't perfect, right? No lab is perfect. Nowhere on earth is it perfect. We are imperfect beings, and we create imperfect machines. So we'll have to account for these all this error that we're going to get, and we have to get a mathematical understanding of it. That's the theoretical yield. The theoretical yield is the amount of product that should form according to stoichiometric calculations. So that's what you would get from your stoichiometry. That's what we calculated in the last screen. The actual yield is what we get in the lab. Now we'll take the two and see how close they are to each other. The percent yield will be the actual yield divided by theoretical yield. This one is not on the formula chart, so I encourage you to commit it to memory. This was on the AP test last year. And we'll multiply. This will give us a value of just this fraction right here will give us a value less than or very close to 1, if it could be a little above, and we'll multiply by 100 to give us a percent. So now, what is the percent error? The percent error is how far away the percent yield is from 100. So if we had a 70% yield, we would have a 30% error. 30% error is actually a really good thing to get in our high school chemistry lab. Honestly, 30% is great. I have gotten 2,000% before, 3,000. So it's 30% is great. So now let's get a mathematical problem of this. In the reaction of 1 mole of methane with an excess of chlorine gas, 83.5 grams of carbon tetrachloride is obtained. What is the theoretical yield, actual yield, and percent yield? Notice that it didn't give you an equation up there, so we'll have to come up with one. What about the actual yield? Did it give you one? It sure did. The actual yield is going to be 83.5 grams. Pretty sweet, right? So it gave us one value. Now we'll find the chemical equation. That's our, it says that we started with methane with an excess of chlorine gas. So that means that chlorine gas was not the limiting reactant. That's what it means by it saying excess. Now, and then it produced carbon tetrachloride, and you would need to figure out that the hydrogen was added on at the end. Fortunately, if you left this off, you would still be able to get the right answer because we only need these three terms. Now we'll do our stoichiometry like before, where we'll take our moles of our known reactant. Since I know it's the limiting reactant, since I know that chlorine is not the limiting reactant, right? And I will take the moles of methane and apply the mole ratio to the moles of my product, and then convert 2 grams and find out my theoretical yield is 154 grams. Do you remember the calculation for percent yield? That would be the actual yield divided by the theoretical yield multiplied by 100 to get 54.2% yield. That's not the best, but it is still pretty good. Okay, we'll start class with this problem out of the textbook, chapter 3, problem number 122. Acrylnitrile is the starting material for many synthetic carpets and fabrics. It is produced by this reaction. If I have this reaction, and if I have these starting materials, the amounts of these three reactants, what mass of acrylnitrile can be produced, assuming 100% yield. Come to class with this at least partially done, if not completely done. Thanks for watching, y'all.